Hello, I hope our technical technical delays, well, sorry for that. Welcome to Writing XS in Plain C. This talk was inspired by an idea suggested to me by Stefan. This talk was inspired by an idea that was given to me by Stefan Mueller. The code samples for this talk are on GitHub. My name is Bulk88. I have a pause ID. I mostly contribute and I'm seen in the Perl community on the P5P mailing list. I use Perl on Windows and I do a lot of Perl Windows C coding and Perl internals coding. This talk is advanced. It assumes you have some C knowledge and at least once tried to code in XS, or you went to Nicholas R's internals talk today. The Perl interpreter is written in C89. It's a large pile of machine code. It is memory unsafe. The Perl interpreter is not written in Java, and it doesn't do JIT internally. There's basically one way to escape the Perl interpreter. You can use JSON RPC and sockets to a daemon written in C. No, I'm kidding. There's two ways to escape the pure Perl language. The first one is XSubs, and the second is by using optree keywords. XSubs can be patched at runtime by swapping the subroutines basically in type globs. Keywords are permanently baked into their callers and cannot be monkey patched at runtime. Perl is also kind of fat, so sometimes you have to use C for speed and performance reasons. XS code is converted to C code by a tool called XSubP, which is currently is a wrapper around xutils parse XS, although originally XSubP was a standalone tool and was not a module that could be reused. XSubP is really old. It's from 1993 from Perl 5 Alpha 4. It's a source code derivative of a tool called TUS, or Type Map User Subs, that was in Perl 5 Alpha 3 in 1993. TUS has even an older predecessor called MUS for Make User Subs, which is from Perl 3 from 1990. So this XSubP is very ancient in its code base. MUS was originally invented by Larry Wall, probably to link to the curses library. It's that old. To understand why the XS syntax just is so confusing compared to modern C, you have to understand that XS was invented during the era of K and RC, not C89, because it's that old. And it was 1 year old when it was invented, so C89 was the newest thing on the block. Also, XS is considered to be macro soup, and the Perl C API is macro soup. There are benefits of using XS versus trying to manually write the C code. You get portability across multiple Perl versions and releases. P5P can optimize the macros and background implementation of the Perl API, and you still have source code compatibility if P5P switches the implementation of the macros. Don't go whining to P5P that your code was broken if you try using anything in this talk, because this is all internal stuff. This isn't the public API of Perl. My examples are from 5.22. The code samples later on probably still work, but there's absolutely no guarantees they work because P5P, this is not the public API of XS. How to make XSubs appear in the Perl language. It's a little complicated. Your PM file calls XS loader or dynaloader. They're almost identical internally. XS loader then calls, in this diagram, the blue boxes are subroutines written in pure Perl, and yellow is written in XS and C code. So XS loader calls DLload file, which is a permanently compiled in XSub in the Perl interpreter. It comes that way out of the box. DLload file calls your OS to load a shared library into your process. The OS shared library loader will return a library pointer back to DLload file DL file then makes this library pointer appear in pure Perl or in the Perl language. The next XS loader takes the module name, it prefixes boot and replaces all colons with underscores to make a C symbol name out of your package. It then again calls the OS shared library loader. It calls DL find symbol. DL find symbol then calls the shared library loader again and looks up the C symbol in your shared library that implements the boot XSub or the main XSub of your shared library. XSubP typically, the code that it generates, it keeps all the XSubs except the boot XSub as static functions, and they are as to not pollute the global symbol table inside the process, which on Windows is the DLL export table, or on Linux is the procedure linkage table and global offset tables. So the boot XSub is the only C function that your shared library has to make externally visible to the rest of the C world inside your process. Once XS loader gets the C function pointer of your XSub, it will call DL install XSub. DL install XSub takes the name of your subroutine that you want. It creates a type and then takes the C function pointer of your XSub. It then creates a type glob and then creates a Perl subroutine inside of that type glob, and now your XSub has appeared in the Perl language, and you can call it. After your XSub appears in the Perl language, your XSub is called, and this is the first time your C code you get control inside the Perl interpreter or Perl process from a C aspect. Almost all boot XSubs will repeatedly call new XS registering additional XSubs in the process. The boot XSub can also often sometimes initializes like global C variables that other XSubs in the shared library are going to reference at some point. Once your boot XSub returns control back to XS loader immediately just returns back to your PM file. Every single Perl XSub on a C level must have this prototype. Now, I said I don't want to show macro soup to all of you, but there is one macro I will be using for the rest of all code samples, which is the PTHX Macro. All XSubs take the PTHX argument, which is a Perl engine pointer, and they drop out the first argument if it's an unthreaded build. So to keep things sane and not have a pile of if-defs, the PTHX macro I included in all slides. It does not exist on unthreaded Perls. Both threaded and unthreaded Perls will take a CV pointer as the second argument, and this is the subroutine on the C side of the Perl engine that represents a sub on the C side. This is the layout of that CV pointer that is the second argument to your XSub. I've colored some interesting fields here. The green fields you interact with as an XS programmer. The red fields, the red members in the CV struct have only meaning to pure Perl subroutines. They have no meaning to an XSub. The yellow stuff you may use sometimes as an XS programmer. Up here we have the C function pointer that is the XSub, and Perl, you write the C function pointer that this is what you compiled up here, the green CV XSub pointer. There's also a second member in the CV struct that's quite interesting to an XS programmer, which is called the any member. This is an unused void pointer by the Perl engine, and it is useful for making like closure XSubs or putting C++ object pointers in here. The any member does not have any backing, storage, or ownership, or reference counting, or any way to free it. So you need to store some sort of other reference to this void pointer elsewhere in your API. Most XS programmers will use the linked list of magic and a free destructor inside your magic vtable in order to free the void pointer, or which would probably be a C++ object pointer that's bound to your XSub. Perl stack has a couple design requirements to implement it the way it is implemented in C. Perl has no strict prototyping, so every single subroutine on a C level is a var arg and can take 0 to infinity arguments incoming, and it can also return 0 to infinity arguments returning. The want array information in pure Perl is passed around on a C level, but it's widely ignored by most XSubs, and most pure Perl code 2 never uses want array. Also, the Perl stack must implement call frames and nesting, because this is basic. This is Perl and not basic, and we don't use gotos to switch function calls. At underscore also has to be switched around. At underscore in pure Perl is actually a view or a window into a much larger array, and a local is done behind the scenes when you do a subroutine call in Perl to move the window of where at underscore is viewing into the Perl stack. In some rare cases, at underscore may also be completely detached from the Perl stack temporarily and then reattached to the Perl stack. This is for like some very rare cases in pure Perl code. At underscore will be detached from the Perl stack. Also, the Perl stack has to be reallocatable at any time because it can grow and it can be reallocated, and that means you can't keep that many pointers, direct pointers into it in your data structures and memory structures, because they may get swapped out from under you. Also, at underscore can grow very, very big, up to 128 terabytes on Linux if you want, but probably nobody wants a very big at underscore. On the Perl stack, all of your incoming arguments also become your outgoing arguments to your caller. You cannot store random pieces of data on the Perl stack. It has to either be a null pointer or a reference counted Perl data structure. You can't store random data on there. Also, context, again, is an artificial concept on the Perl stack. It's simply the number of arguments coming in or coming out of that subroutine. And the want array information is available through a C function call that inspects the stack and some other secret fields. How the Perl stack is designed. The Perl stack is stored in a Perl global variable. The start of it is stored in a global variable called PL mark stack. It's stored in PL stack base, and when all XSubs and all pure Perl subs heavily interact with the Perl stack and the mark stack in order to know where their section of the Perl stack starts and where their incoming arguments are and their outgoing arguments are. In order to know where your section of the Perl stack starts, not your caller's section, which is private, but your section, you have to look on the mark stack under mark stack PTR. And in this diagram, the red fields are memory that you can't touch. It's invalid for you. The yellow fields are shared between you and either your caller or your callee. And the green fields are technically private to you. But you have to read the mark stack PTR and get the I32, which is an index into the Perl stack, off of the mark stack. You then combine, you add the index to PL stack base, doing pointer arithmetic to compute an absolute pointer into the Perl stack. This is now called the mark pointer, and the mark pointer is referred in a lot of XSubP generated code, but the memory that is underneath the mark pointer is never your memory. Question? It's technically, the memory slot belongs to the caller, but it's uninitialized for your purpose as a subroutine. Finally, we have PL stack SP, which is an absolute address into the Perl stack. And if Perl stack SP is equal to the mark pointer, you receive 0 incoming elements, and therefore there's nothing to read underneath PL stack SP. If PL stack SP is ahead of the mark pointer, then you got incoming elements. Theoretically, an XSub could also allocate some more Perl stack, the green zone, and have a private pile of scalar SV pointers that are completely invisible to the caller and callee, but everyone just uses C autos and regular C vars to store SV pointers in XS code. There's really no point of using the Perl stack. You just use a C auto to store a scalar locally. And then finally, on the right side, the second block of yellow entries on the Perl stack would be your outgoing arguments to your callees if an XSub is calling back into the Perl engine or is calling another Perl subroutine. You also have to remember whenever you read or write to the Perl stack, you have to bounds check so you don't run off the end of it or you're not reading uninitialized slices on the Perl stack, because if you go, some cases, if you take a C debugger and you sometimes dump even the piece of Perl stack before you, you may find completely uninitialized pointers in there. There's no guarantee the red zones will ever even have valid data, even if there's no required. Your caller is supposed to keep valid SV pointers on the Perl stack, but sometimes I've noticed the Perl interpreter just puts garbage on there, or it just allocates up a chunk of Perl stack and never fills in anything. The smallest XSub you can possibly write in plain C is the following. Every XSub has only one API contract obligation, which is to decrease the mark stack pointer, to wipe that index slot that it received in. This is the smallest possible XSub you can write in plain C without crashing the Perl interpreter. All it does is returns @ underscore to the caller, because the incoming arguments also become your outgoing arguments if you don't change anything. Now let's do something a little more complicated let's write a more complicated XSub in plain C, or counting the number of items in @ underscore. Every single XSub is going to generally have the following prologue at the start. We first read PL stack SP, or the global stack pointer, into a C auto. We then have to read our I32 index into the mark stack, into the Perl stack, read our index off the mark stack. We then compute the mark pointer by adding the index to the start of the Perl stack, and then by subtracting our local S stack pointer from mark pointer, and this is again pointer arithmetic, so it's actually a divide by 4, divide by 8 using pointer arithmetic by the C standard. We can compute the number of items we received, and then we have our API contract obligation of removing one slot off the mark stack. Now we have to return the number of @ underscore, to return a count back to our caller. We have to create a new Perl scalar down here. Now, the Perl stack does not own any reference counted scalars on it, or hashes or arrays. Nothing on the Perl stack is owned by the Perl stack. Some other data structure in your process must have ownership of every pointer on the Perl stack. If you don't know what is supposed to own a scalar that's on the Perl stack, you can put it on the Mortal stack, which is a temporary stack that owns various scalars, and they're generally freed at the next semicolon or closing curly. We then, after we've created our new scalar that we're going to return to our caller, and we make sure we don't leak it because it's mortalized, we then set it to the item count that we computed earlier. Now we have to, because we could have gotten 0 to infinity items, we have to wipe all of our incoming arguments by assigning mark to SP, so when mark is equal to SP, there's 0 incoming arguments or outgoing arguments. We then have to bounds check the Perl stack, because if we were called with 0 arguments, we can overflow by returning 1 argument when we really have nothing on the Perl stack. It's empty, and we were at the end of the memory allocation limit. So we bounds check the size of the Perl stack, and we reallocate the Perl stack if it's too small. We then advance the stack pointer by 1, because remember, if mark is equal to SP, it's an invalid memory address. That's our caller's address. That's not our memory slot. So we advance SP by 1. We write the new SV pointer to the Perl stack, and then we update the global copy of the stack pointer so our caller knows how many arguments we returned. And then we return back to the Perl engine. How to print a scalar. Again, we have the exact same prologue you saw earlier. The reason you use XSubP and you use all the macros is because nobody wants to write 5 statements every single time for every single XSub. Again, we have to back up our mark stack, delete one slice. This time we check the item count. If we don't have the right number of items, we have to fatally die. Again, you never know in an XSub how many incoming arguments you got. There's no enforcement. Everything is var arg. So you always have to check how many incoming arguments you get. Because we know we got one item, we can safely read SP and just absolutely dereference it and read the scalar pointer off the Perl stack. Then we have to check if our scalar internally is a string or not. If it's a string, we can directly read it. Otherwise, we have to call a casting function, which is sv to pv flags. Again, this is a macro in the official API, but here I expanded it so you kind of understand the internals of the macro. And finally, we call printf to print the char pointer that we pulled out of the scalar. Now, because earlier we checked the items count, we can safely lower the stack pointer by 1 slot, and then we copy the local stack pointer back to the global so that we are returning an empty list to our caller. The reason I can safely back up SP is, again, we checked the items count earlier, so you don't need to check twice where SP is. You just can absolutely do a -1, and you know it's going to work because we checked earlier that we have only 1 slice. Summing a list in a loop, so this would be iterating over an incoming list in our XSub. Again, we have to have this prologue at the start, but this time we back up stack pointer by the number of items. Again, there's pointer arithmetic. Items is in array slots, while SSP is an absolute pointer, but due to the magic of pointer arithmetic in C, there's automatic, like divide by 4 or times 4, or divide by 8 or times 8. We loop over the incoming list, but you'll notice that SP, there's a +1 going on. And that's because when we backed up SP by the number of items, SP actually is equal to mark, and mark is an invalid memory address. So when we dereference the stack pointer, we're always doing +1 because of the way the mark stack, the mark pointer never is a valid memory address. So 0 is always basically invalid, and we just do a +1 to read off. Now remember, for the summing the list, we could have gotten, again, 0 incoming arguments. So this for loop may never even run. Similar to the the string example earlier, we have to check the flags for each scalar. If it's a double, we can directly read the double value out of the scalar. Otherwise, we have to call the casting function again. And because we could have gotten, again, an empty incoming list, we have to grow the Perl stack, bounce check the Perl stack to make sure we can return 1 element. We then create a new Perl scalar. In this case, instead of calling SV new mortal, I mortalize or add the mortal flag and the background, the Perl background checking, whatever, by calling SV2 mortal, which takes an existing scalar pointer and then marks it for proper destruction based on the behavior semantics of the mortal stack. We then, is the sound actually okay? We then assign the scalar SV pointer to the Perl stack, and we copy our local Perl stack back to the global Perl stack, and then we return back control back to the Perl engine. Earlier, I conceptually showed a boot XSub with the yellow and blue diagram, but this is how an XSub is actually written in plain C. We have the small prototype, the small prologue at the start. We have to back up the mark stack again, which is our API contract obligation, by assigning mark to the global SP. we wipe all incoming arguments, returning an empty list to our caller. Just as in the diagram earlier, new XS is just called repeatedly with the string name of the subroutine we want to register and its pointer as the second argument, and the third argument is the source code file name for things like warnings. Although the warning system is not actually smart enough to return .c's for most warnings. It'll just return the last pure Perl line you ran, which is, for performance reasons, P5P has never wanted to try to have warnings return errors from .c files and line numbers inside C files. Instead, it just accidentally does record, it tells you the last pure Perl line ran. It's sometimes confusing for debugging because you think the fault is on a pure Perl line when it's actually inside an XSub, but without a C debugger, you can't tell whether it's from an XSub or from a pure Perl subroutine, the warning or the fatal die message. How are we on time? Oh, great. We have time. Now for some really crazy stuff. It'll get crazier. This is a pure Perl version of the following plain C XS code I'll explain later on for how an XSub can call an XSub without ever going through the Perl engine. So it's a C XSub calling a C XSub without any help from Perl, and no Perl machine code is involved. Here we have a typical prologue. Every single XSub has this prologue, and we back up mark stack. In order to call a child XSub, we have to create our own mark stack entry. So we have to bounce check and advance the mark stack pointer. Then we have to compute the start of the next, our outgoing section of Perl stack. And that's done by taking SP. You create that index number again. You then assign the index to the global, put it on the global mark stack. Then we have to grow the Perl stack because we have to create outgoing elements. This XSub simply copies the incoming arguments and repeatedly sends them to callees as outgoing arguments. Now, remember that all outgoing arguments become your incoming arguments from your child calls. So every time you send arguments out to a child call, when controllers return back to you, your outgoing arguments were wiped. So to push the same list or to multiple child calls, you have to keep putting it back on the Perl stack after every child call, because the outgoing section of Perl stack is basically either uninitialized memory or the returned list from your child call. So we do a mem copy, taking our incoming section of Perl stack, and we copy it to our outgoing section of Perl stack. We then advance the Perl stack pointer ahead of the start of the outgoing section of Perl stack. Now, in order to call a XSub, we have to get the CV pointer that's associated with that C symbol. So we call Perl get CVN, which does a lookup in the symbol glob symbol stash tree of Perl and gets the CV pointer associated with that C XSub function. We then can directly call that XSub, although this is a plain C to C call, even though the CV pointer is required as the second argument in the myCountArgs, which is a C function. It's in the same shared library, but we have to get that CV pointer. A lot of XSubs never look at the second argument, but don't assume that the second argument won't be dereferenced for, let's say, that any example or for iterating the. Usually, the any example is going to crash if you put the second argument instead of being the proper CV pointer. It's null, any XSub that uses the any member is going to crash when it dereferences its CV pointer, which would be null. So that's a bit of a hack. Some Perl code passes null, but that's a bad thing to do. Please pass the real CV pointer. After we call the child XSub, we have to again fetch from global PL stack SP the global stack pointer, reassign it to our local SP, and then based on the saved index earlier, we can compute how many arguments we got. If we didn't get one argument from counting the number from this list count XSub, if we didn't get one item in list context, we fatally error. We then can, after we've checked we got one element returned from our XSub, we can read SP directly and get the count SV, which is at the bottom. We then back up SP by 1 to wipe the one element that we got from our child call. Now we have to call again. Now because we already once pushed the mark pointer on, we can just again put the index number back on mark stack, and we don't need to balance check the mark stack because the mark stack and the Perl stack will never shrink during a child call. They can only get bigger or get reallocated. They'll never shrink backwards. We have to again recompute the mark pointer because we don't know if our child call reallocated the Perl stack. We then again copy our incoming section of Perl stack to the outgoing section of Perl stack with a mem copy, because every single child call wipes all the arguments that you send it, because the same exact zone that is used for outgoing arguments is used for incoming arguments or returned arguments. Again, we have to get the CV pointer, and we directly call the XSub with its CV pointer. We again have to fetch PL stack as we have to again read the global stack pointer, recompute how many items we got. If the sum, if we didn't get one item, we can never trust any XSub or any subroutine to return a certain number of items. In Perl, you just get undefs, but in C, you will crash in XS if you try to dereference and there weren't enough elements returned. Again, we read SP pointer directly, getting the SV pointer off the Perl stack, and then we back up the SP pointer by 1, wiping the one argument. Finally, once we have gotten our 2 SVs from our 2 child calls, we can create a third scalar of the count and the sum of our incoming list that we were passing to our child calls. We immortalize it again to make sure we're not leaking a scalar. And finally, to print the scalar we just created, we have to again put the index on the mark stack, advance the mark stack, advance the stack pointer to, because we have one outgoing element, we write our new scalar SV pointer to the Perl stack, and then we put the local Perl stack on the global Perl stack. Again, we get the CV pointer and directly call the XSub directly through the C to C without going through Perl or the call SV call in the Perl API. Again, we have to recompute mark because PL stack if you try to use SP or mark after any other subroutine calls, you will crash, and it's a common problem on P5P and with CPAN code of where you use stale local SPs and stale local mark pointers, and after doing a call to a child subroutine, you never refresh those pointers from global storage or from the global interpreter variables, and then it's a use after free error, and or use after realloc error, and you promptly crash. In order to return an empty list, again we assign mark to the global SP, and we return and we've returned an empty list to our caller. Questions? Go ahead. If you actually do this in production, writing all this code by hand, you should be fired for wasting your boss's money. Is it significantly faster to write XS code in plain C versus using XSubP and the template system? And the answer is clearly no. Use XSubP and Swig and whatever other tools you want. This is like the worst possible way to write. The worst possible way to write an XS extension, short of flicking light switches on your PDP-11 in machine code. What's your budget for your software project? Any other questions? Go ahead. Call SV is capable of running Optree pure Perl code. If you call an XSub directly from an XSub, it's a C2C function call, and it's absolutely impossible to run a pure Perl subroutine or monkey patch it by doing an eval and just swapping out the subroutine at runtime. You can't do that if it's permanently wired function pointer to function pointer. So call SV will either call another XSub, or it will call the keyword Optree. It will an Optree-based subroutine, and it will again look through the Perl stash glob tree. The question is, can you look in the CV directly and extract the XSub C function pointer and call that directly? The answer is yes. There is a set of Perl macros called MultiCall, which is faster than using call SV, and it attempts to look at the flags of the CV and determine if it's XSub based or whether it's pure Perl based, and it offers less overhead than call SV. It's called MultiCall, and it's a complex set of header files and more macro soup, but it creates a call frame directly in C without using C function pointers in the Perl engine. If it's Optree based or pure Perl, you clearly have to call back into the Perl engine, but it's called MultiCall if you want to Google it. Any other questions? Well, thank you for me dividing by zero your brain.